All right, welcome to Unit 2, and here's our first lesson, Lesson 1. Our unit on congruence. We'll start off by asking the question why we move things around. So, given two segments, AB and CD, which could be very far apart, how can we find out if they have the same length without measuring them individually? Do you think they have the same length? How would you check? And we will revisit this question later. For example, given a quadrilateral A, B, C, and D, where all four angles at A, B, C, and D are right angles, are the opposite sides AD and BC of equal length. Later, we will prove that they have the same length. Similarly, given angles AOB and angle A prime, O prime, B prime, how can we tell whether they have the same degree without having to measure each angle individually? For example, if two lines L and L prime are parallel and they are intersected by another line, how can we tell if angles A and angle B, as shown, have the same degree when measured? We are therefore confronted with having two geometric figures, whether it be two segments, two angles, two triangles, etc., in different parts of the plane, and we have to find out if they are, in some sense, the same, meaning same length, same degree, and same shape. To this end, there are three standard moves we can use to bring one figure on top of another to see if they coincide. So the key question is, how do we move things around in a plane, keeping in mind that lines are still lines after being moved, and that lengths of segments and degrees of the measures of angles remain unchanged in the process. Moving things around in a plane is exactly where the concept of transformation comes in. So a transformation of the plane, to be denoted by F, is a rule that associates or assigns to each point P of the plane a unique point which will be denoted by F of P. So by definition, the symbol F of P denotes a single point unambiguously. That means without doubt. The symbol F of P indicates clearly that F moves P to F of P. The point F of P will be called the image of P by F. And we also say that F maps P to F of P. The reason for the image terminology is that one can intuitively think of the plane as a sheet of overhead projector transparency or as a sheet of paper. A transformation F of the plane is a projection, literally using a light source, from one sheet of the transparency to a sheet of paper with the two sheets identified as being on the same plane. Then the point F of P is the image on the sheet of paper when the light source projects the point P from the transparency. So if you notice, this is our light source right here. And here is our overhead transparency. When the light shines through, if this is point P and this is point Q, then point P is being projected onto the wall or screen or another piece of paper. It is projecting F of P. Same thing with Q. If this is point Q, then the projection of Q would be called F of Q because it's in a different part of the plane. As to the map terminology, think of how you would draw a street map. Drawing a map is a complicated process, but the most mathematically accurate description for the purpose of school mathematics may be that one starts with an aerial view of a particular portion of a city. In the picture below, we look at the area surrounding the Empire State Building, which is ESB on the map, in New York City. The picture reduces the three-dimensional information into 2 dimensions and then maps each point on the street to a point on your paper, which is called the map. A point on the street becomes a point on your paper, so you are mapping each point on the street to your paper. Transformations can be defined on spaces of any dimension, but for now we are only concerned with transformations in the plane. In the sense that the transformations are those that assign a point of the plane to another point in the plane. Transformations can be complicated, meaning the rule in question can be quite convoluted. But for now, we are concentrating on only the simplest transformations, namely those that preserve distance. So a transformation f preserves distance or is distance preserving if given any 2 points p and q, the distance between the images f of p and f of q is the same as the distance between the original points p and q. And if you want to go back to that transparency example, that's what this is describing. An obvious example of this kind of transformation is called the identity transformation, which assigns each point p of the plane to p itself. The main purpose of this module is to introduce many other distance-preserving transformations and show why they are important in geometry. A distance-preserving transformation is called a rigid motion, or an isometry, that, as the name suggests, moves the points of a plane around in a rigid fashion. Alright, so here's your exploratory challenge. Complete the problems using your transparency to explain how you would map one figure onto another. Once you are done with this, go ahead and continue the video. Alright, so we will go over these in class, but to wrap up this lesson, we can use a transparency to represent the plane and move figures around. We can check to see if one figure is the same as another by mapping one figure onto another and checking to see if they coincide. And last, a transformation that preserves distance is known as a rigid motion, meaning the distance between 2 points is the same after the transformation is performed. So a transformation of the plane denoted by f is a rule that assigns to each point p in the plane one and only one unique point, which will be denoted by f of p. And here are the parts of that definition summarized again. And last, if given any 2 points p and q, the distance between the images f of p and f of q is the same as the distance between the original points p and q. Then the transformation f preserves distance or is distance preserving. And last, a distance preserving transformation is called a rigid motion or an isometry, and the name suggests that we move points around the plane in a rigid fashion. All right, we'll see you in class.